All right, hello everyone, and welcome to my channel. This is a channel for educational purposes, and we look at great theories of everything. In this case, today is our 501st video that we've done on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson proposed his two fundamental postulates in about 1959. And from there, he derived a theoretical universe, what his universe would look like if his postulates were correct. And then he, in books like the one we have in front of us today, he compares his theoretical universe with the measured empirical universe of the legacy scientists. And this book today is called Basic Properties of Matter. And this book's on chemistry. Larson arrives at equations for many of the basic properties of matter, like the melting point or the compressibility, and then compares his results with the scientific tables. And we are about to start chapter 17 of this book, which is called Ionization. Now, if you don't know anything about the reciprocal system, you want to watch one of my first 474 videos on this subject, where I go into at least a little bit of detail, enough to get you up to speed, to be able to follow along, I think. And but for the purposes of this video, I'm going to assume that you have at least some kind of working knowledge of the reciprocal system. I'll go over the first postulate. Larson was a proponent of a universe made entirely of motion. Other theorists have come up with that before, but Larson made it work, turned it into a generalized theory, because he defined motion in a way that was unprecedented. So in Larson's system, the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so the universe is made out of motion. In particular, we're talking about a kind of motion that Larson refers to as scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. You can use something like a balloon that you put dots on with a magic marker. If you blow up the balloon, all the dots will be moving away from each other. They will all be moving in every direction away from each other, but they're not moving in any specific direction. And then if you contract that balloon, they will all be moving toward each other, but again, not in any specific direction, in all directions inward. Larson refers to the outward motion as the progression, the inward motion as gravitation. The progression is really the source of everything in Larson's universe, and is manifested by taking that source and reversing it, and turning that outward motion of the balloon into an inward motion, which is gravitation, which is inherent in matter. And then Larson defines motion as the relationship between space and time. So, for example, you have speed. Speed is, the person is running at 10 miles per hour, 10 miles of space in 1 hour of time. Space over time. So in this case, speed is space divided by time. All of our scientific phenomena are forms of motion, and therefore they all can be defined in exclusively in space-time terms, a fraction with space or time as the numerator, time or space as the denominator. But space and time can have exponents. So, for example, matter in Larson's system is time to the third power over space to the third power. And energy is simply time over space. Acceleration is space over time to the second power. Force is time over space to the second power, and so on. And since the universe is quantized, everything is in discrete units. All of our scientific quantities can be quantized. They come in units. You can have a unit of motion, in a unit of speed, a unit of energy, a unit of matter, and so on. Okay, now when we talk about his electronic theory, which we're going to do here in this chapter, Larson's electron is a little bit different than the legacy electron, because Larson's electron is naturally uncharged. So we have the uncharged electron, which, like everything else in Larson's system, is a kind of motion. It is a rotating unit of space moving through matter. Matter is primarily made out of time, and so space, the relationship of space to time, is motion. And so the unit of space, the electron, naturally moves through matter in the same way that matter moves through space. They are mutual motions. And the electron moving through space is known as electric current. This is an uncharged, the electron moving through matter is electric current. The uncharged electron moving through matter is electric current. And so the electric current is uncharged. Now, the electron can take a charge, but a charge is not an electron. Charge is a kind of motion, just like everything else in Larson's system. And a charge is a rotational vibration. And an electron can take a charge, a rotational vibration, in which case it becomes static electricity, and it becomes charged. And that static electricity tends to stay on the surface of the matter because it has more trouble moving through the matter, because now the electric charge is a time over space kind of motion, and so it doesn't move readily through time, because the relationship of time to time is not motion. It's only the relationship of time to space that's motion. Okay, now with this background, and again, if you want to watch one of my first 474 videos, that will flesh out a little bit more. But let's start here at chapter 17, ionization. Electric charges are not confined to electrons. Units of rotational vibration that constitute electric charge may also be imparted to any other rotational combination, including atoms, as well as other subatomic particles. The process of producing such charges is known as ionization, and electrically charged atoms or molecules are called ions. Like the electrons, sorry, I lost my spot there. I think I'm pressing the wrong button here. Let's get back to the beginning here. Okay. Like the electrons, atoms or molecules can be charged or ionized by any number of agencies, including radiation, thermal motion, other physical contact, etc. Essentially, the ionization process is simply a transfer of energy, and any kind of energy will serve the purpose if it is delivered to the right place and in the necessary concentration. As indicated above, one of the sources from which the ionization energy can be derived is the thermal energy of the ionizable matter itself. We saw in Chapter 5 that the thermal motion is always directed outward. It therefore joins with ionization in opposition to the basic inward rotational motions of the atoms, and is to some degree interchangeable with ionization. The magnitude of the energy required to ionize matter varies with the structure of the atom and with the existing level of ionization. Each element therefore has a series of ionization levels corresponding to successive units of rotational vibration. When the thermal energy concentration, or the temperature, of an aggregate reaches such a level, the impacts to which the atoms are subjected are sufficiently energetic to cause some of the linear thermal motion to be transferred into rotational vibration, thus ionizing some of the atoms. Further rise in temperature results in ionization of additional atoms of the aggregate, and in additional ionization, more charges on the same atoms, and in additional ionization of previously ionized matter. Thermal ionization is only of minor importance in the terrestrial environment, but at the high temperatures prevailing in the sun and other stars, thermally ionized atoms, including positively charged atoms of division 4 elements, are plentiful. Again, Larson uses the asterisk to denote that he is using the conventional terminology, but that in his terminology it would be the opposite. So he uses that on positive and negative. The ionization condition is, in fact, normal at these temperatures and at each of the stellar locations. There is a general ionization level determined by the temperature. At the surface of the Earth, the electric ionization level is 0, and except for some special cases among the subatomic particles, any atom or particle that acquires a charge while in the gaseous state is in an unstable condition. It therefore eliminates the charge at the first opportunity. In some other region where the prevailing temperature corresponds to an ionization level of 2 units, for example, the doubly ionized state is the most stable condition, and any atoms that are above or below this degree of ionization tend to eliminate or acquire charges to the extent necessary to reach this stable level. Since the rotational vibration that we know as ionization is basically a motion in opposition to the rotational motion of the atom, the ionization cannot exceed the net effective positive displacement, or the atomic number. In a region where the ionization level is very high, the heavier elements therefore have a considerably larger content of positive displacement in the form of ionization at a given temperature than those of smaller mass. This point has an important bearing on the life cycle of the elements and will be given further consideration later. In the nuclear theory of atomic structure, currently accepted by the physicists, the atomic, quote, nucleus is surrounded by a number of electrons equal to the atomic number of the element. Ionization is viewed as a process of detaching electrons from the atom. On this basis, the maximum degree of ionization is attained when all electrons have been removed and only the bare nucleus remains. This is a plausible hypothesis, and on first consideration, its plausibility would appear to be a point in favor of the nuclear theory. It should be realized, however, that any reliable theory of atomic structure will have essentially the same explanation of ionization, differing only in the language in which it is expressed. Such a theory must identify entities that are added to or removed from the atoms as the atomic number increases. Successive addition or elimination of these entities then explains ionization. In the nuclear theory, which views the atoms as a collection of particles, these entities are electrons. In the theory of the universe of motion, which finds the atom to be a combination of motions, they are units of rotational motion. Any other theory that might be formulated would necessarily have to identify some entity that could similarly be added or removed unit by unit. Thus, the ionization process would be consistent with any theory. Consequently, it gives support to none. Just to recall, Larson's theory of atomic physics, he does not have a nucleus in his atom. Basically, the nucleus of the atom is the entire atom, and that what is known as the electron cloud, all of the space there, that empty space where the electrons are supposed to be rotating, is no such thing. It is actually the interatomic distance. So that is actually in the solid state in legacy science. The atoms are touching each other, but in Larson's system, in the solid state, atoms are a great distance apart, and they find an interatomic equilibrium and an interatomic distance, equilibrium distance apart, and that distance apart is what is known as the electron cloud by the legacy scientists. So one of Larson's earliest books is actually called The Case Against the Nuclear Atom. So in Larson's system, there is no nucleus. What's thought of as the nucleus is actually the whole atom. So the atom is much smaller than the legacy science atom. Okay, back to the text. In the terrestrial environment, each ionization level of each element has a specific ionization potential that represents the amount of energy required in order to accomplish the ionization. It is currently assumed that these values are fixed natural relations and therefore constant for all environments. The theoretical status of this assumption in the context of the reciprocal system of theory has not yet been clarified. It may well be valid throughout the gaseous state. However, the measured ionization levels are obviously not applicable to ionization in the condensed gas state, the state in which the gas molecules are within the equivalent of unit distance of each other. In Larson's system, space, time, and motion are quantized, so there is a minimum unit of space and a minimum unit of time. and yeah, you can't get any closer than a minimal than 1 unit of space. So he says that atoms are within the equivalent of unit distance of each other. That basically means that they are 1 unit of space apart, but then if they are 1 unit of space apart, they can't move any closer in space. So what they do instead is they move farther apart in time, which is the equivalent of moving closer together in space because of the reciprocal relationship between space and time. The outward motion in time is equivalent to an inward motion in space. But the motion really occurs in time because it can occur in space because it's already at the minimum 1 unit of space. The physical relations in this state are very different, in this condensed gas state, are very different from those in an ordinary gas, including reversal of all scalar directions. Larson calls that the time region. When you are in less than 1 unit of space, then you're no longer in space, and you are in what he calls the time region. And when you go into the time region, you get the reversal of the progression, and the progression is now inward in space, or in equivalent space, and gravitation is outward in equivalent space. Thus, all that we can now say about the ionization potential in this state is that each successive level of ionization must involve an increase in energy. As we will see in Volume 3, the matter in most of the observed stars is in the condensed gas state. The relation between temperature and the degree of ionization enables using the ionization, which can be observed spectroscopically, as a measure of the surface temperature of the stars. For example, below 12,000 K, helium is not ionized. At about 35,000 K, it is mainly in the form of helium-2, singly ionized. At still higher temperatures, it is doubly ionized, He3. Other elements have similar ionization patterns, and the mixture of ions observed in the spectrum of a star thus indicates the range of temperatures at its surface. The O stars, which are in the range up to about 80,000 degrees Kelvin, are reported to contain N2, nitrogen-2, oxygen-2, carbon-2, and silicon-3, as well as helium and hydrogen ions. It should be understood, however, that this relation between ionization and temperature holds good only where the ionization is produced thermally. References are made in the astronomical literature to ionization temperatures, but these are merely the temperature equivalents of the ionization levels. Unless the ionization is thermally produced, they do not indicate the actual temperature. The level of ionization is a reflection of the strength of the ionizing agency, whatever it may be. If that agency is the thermal energy, then the ionization is a measure of the temperature. But if the ionizing agency is radiation, the ionization level is a measure of the strength of the radiation, not the temperature. In Volume 3, which is on astronomy, that's the book called Universe of Motion. So in Volume 3, we will encounter the same kind of misconception in dealing with the relation between temperature and the production of X-rays. When the X-rays are thermally produced, there is actually a relation between the X-ray emission and the temperature. But here, again, if the X-rays are produced by some other agency, the relation is between the X-ray emission and the strength of that other agency, and it is independent of the temperature. The importance of this point lies in the fact that the emission of X-rays is currently being treated as an indication of high temperature in cases where the nature of the X-ray production process is unknown, even in cases where the conditions are such that the temperatures necessary for thermal production of X-rays are impossible. Temperatures in the millions of degrees are inferred from X-ray observations in locations where the actual temperature cannot be more than a few degrees above absolute zero. Temperature, without a qualifying adjective, is a specifically defined concept, and it is temperature as thus defined that enters into the various thermal relations. The use of other kinds of temperature is entirely in order, providing that each is clearly defined and is identified by an appropriate adjective in an expression such as ionization temperature. In fact, we will introduce such an alternate kind of temperature, a magnetic temperature, in Chapter 24. But it should be recognized that these temperatures have their own sets of properties. The thermal relations do not apply to them. For example, the general gas law applies only to temperature in the usual thermal sense. This law is expressed as PV equals RT, where P is the pressure, V is the volume, T is the temperature, and R is the gas constant. From this law, it is apparent that a high temperature can be developed in a given volume of gas only under high pressure. In interstellar and intergalactic space, the pressure acting on the extremely tenuous medium is near zero. And from the general gas law, it is evident that the temperature must be at a correspondingly low level. The temperatures in the millions of degrees that are currently being reported from these regions are totally unrealistic if they are intended to mean temperature in the thermal sense. Some of the existing confusion in this area appears to be due to a failure to draw a clear distinction between the two types of vectorial motion in which the particles of a gas participate. These constituent particles share in the translational motion of a gaseous aggregate as a whole, and it is generally understood that this is not a thermal motion. That is, a fast-moving aggregate must be relatively cool. An atom or particle moving independently in space is subject to the same considerations. Its free translational motion has no thermal significance. The thermal motion is a product of containment. It is the directionally distributed random motion that results from the restriction of the motion to the volume within certain limits. The pressure is a measure of the containment. The temperature, the measure of the thermal motion, is therefore a function of the pressure as indicated in the gas laws. High temperatures can only be attained under high pressures. If part or all of the gas in an aggregate escapes from confinement, its constituents move outward unidirectionally, and the thermal motion is converted to linear translational motion. The temperature and pressures decrease accordingly. The picture of the nature of electric charges and ionization that we derive from the postulates of the theory of the universe of motion is very different from the currently accepted explanation of these phenomena, which is an outgrowth of hypotheses formulated in the early days of electrical investigation on the basis of the limited amount of empirical information then available. The early investigators in this area identified negative asterisk charges with electrons and positive asterisk charges with atoms of matter. Meanwhile, it was found that the atoms of certain elements undergo spontaneous disintegration in which electrons are emitted along with other products. On the basis of these empirical findings, the scientific community adopted the hypothesis previously mentioned in which positive asterisk charges are attributed to an atomic nucleus, and negative asterisk charges entirely to electrons. Positive asterisk and negative asterisk ionizations were then ascribed to deficiency or excess of electrons, respectively. One disturbing feature of this explanation was the great disparity in the sizes of the units of the two entities that were identified as the carriers of the charges. The roles to be played by positive asterisk and negative asterisk charges in the theory were essentially reciprocal in nature, yet the presumed carrier of the positive asterisk charge, the proton, has nearly 2,000 times the mass of the negatively asterisk charged particle, the electron. Physicists were therefore greatly relieved when the positive asterisk analog of the electron, the positron, was discovered. It does not seem to be generally appreciated that this discovery, which restored the symmetry that we have come to expect in nature, has destroyed the foundation of orthodox theory. It is now evident that positive asterisk charge is as much of a reality as negative asterisk charge. It is not merely an electron deficiency, as the theory contends. Okay, we're going to leave it there for today and resume looking at Chapter 17 on ionization tomorrow. Just remember that this is a generalized theory. The reciprocal system is a generalized theory. And so we're learning about chemistry here, about ionization, but what we learn in these lessons can be applied universally to other fields. And so we're not, specifically learning about chemistry. We're learning about how the theory is applied and how to use it in your own life. All right. Thanks for tuning in.